Traditional antivirus systems rely on known, static code signatures to catch threats. But in response, modern cybercriminals use string encryption and advanced obfuscation techniques to completely scramble those signatures into unrecognizable noise. The standard countermeasure is dynamic analysis, actually running the malware in an isolated environment to observe its behavior. But executing code to see what it does demands massive amounts of time and computational power. This split-screen comparison shows an alternative approach. On the left, a standard text scan fails against the obfuscation. But on the right, we convert that exact binary code into a two-dimensional image. Machine learning detects the structural texture, even when text is hidden. By building this Python-based visual pipeline, we skip the execution step completely. We shift malware detection from a reactive game of guessing signatures into proactive pattern recognition. Step 1 of this pipeline is extracting the data. We take the target Android application, the .apk file, and unzip it just like a standard archive folder. Inside those unzipped contents, we need to locate one specific file, classes.dex. This is the Dalvik bytecode, the actual runnable engine of the application. Here is what the interior of that file looks like to a machine before any conversion takes place. The 010 editor interface displays the raw decimal and hexadecimal data, mapping out the header. Look deeper into the editor, and that data breaks down into pure 8-bit binary sequences of zeros and ones. Extracting specifically the classes.dex file is mandatory because it contains every operating instruction the app will ever execute. It is the definitive, untamperable source of truth. To turn those zeros and ones into an image, we have to follow strict mathematical rules based on file size. Raw binary data cannot be forced into an arbitrary square. Looking at this dimension table, we start at the baseline. Files under 10 kilobytes form a 32 by 32 pixel matrix. As files grow, dimensions scale up proportionally, scaling all the way to the maximum extreme of a massive 1024 by 1024 grid. If you ignore these rules and attempt to force data into incompatible dimensions, Python will trigger a value error and instantly crash your machine learning classifier. Now we build the script. First, we instruct the script to import the numpy and matplotlib.pyplot libraries. Next, we tell the script to read the extracted classes.dex file entirely as raw bytes. This diagram illustrates the core mathematical conversion. We translate those bytes into an 8-bit binary vector, assigning a value of 0 for a black pixel, 255 for a white pixel, and the spectrum between them as grayscale. We then use the numpy.reshape function to snap that linear array of pixels into the strict matrix dimensions we defined in the previous step. The final code step uses matplotlib to export and save the populated matrix locally as a .jpg image file. This workflow diagram shows the complete pipeline. We have taken a folder of dense, unreadable binaries and converted them into a clean dataset of structural images, ready for AI analysis. Feeding raw, high-resolution image matrices directly into a machine learning classifier without preparation introduces systemic risk and slows down the computation. Before training begins, we have to normalize the images so all pixel values conform to standard uniform values. As you can see in this model, we then apply principal component analysis, or PCA, via scikit-learn. The data collapses along principal axes, mathematically stripping away feature noise while preserving the core structural data. With the data normalized and reduced, we pass it into an XGBoost classifier for training. Researchers running this pipeline found an optimal configuration. Regardless of the original file size, scaling and analyzing images at a 256 by 256 matrix yields the absolute highest detection accuracy, maxing out at 95%. The finished pipeline operates at extreme speed. Dropping a new APK into the script generates an image and outputs an XGBoost classification in a fraction of a second. If you want to train a model right now without building the extraction script, researchers have released the AndroDex dataset. It provides over 21,000 pre-processed images publicly available for analysis. This grid illustrates the 4 specific classifications contained within the dataset: benign, malware, obfuscated benign, and obfuscated malware. That third category, obfuscated benign, is crucial. Legitimate app developers frequently hide their code to protect their intellectual property. Training the machine learning model to recognize this specific texture, prevents it from falsely flagging clean apps as malware. By utilizing visual code mapping and the AndroDex dataset, engineers completely bypass string encryption. We neutralize modern evasion techniques by securing systems through mathematical structure, rather than relying on easily hidden signatures.